This is terrifying. I've disconnected the main earthing conductor, and not only is the main earthing terminal live, this water pipe is also live, and so are all the exposed conductive parts of this installation, as are all the exposed and extraneous conductive parts in the house next door. And worst of all, I carried out the safe isolation procedure, and I'm still potentially dead. So what's gone wrong? And was there anything I could have done to protect myself from this? We're going to discuss 4 different areas where safe isolation may not be quite as safe as you might think. Let's get into diverted neutral currents, alternative sources of supply, signs of energy theft, and damage to the one part of the electrical installation no eFix viewer would ever dream of touching, the part that causes engineers to turn up dressed for the hurt locker. It's the service head. And before we start, a very quick thanks to TIS and Ludum Palazzoli for supporting the creation of this content. First up, as we showed in our introduction, we've stumbled across the much discussed neutral current diversion that's becoming an increasing scourge to properties, people, and electricians. It occurs when there's a problem outside your property, and it's also outside the control of you, the electrician, or the property owner. The vast majority of properties in the UK are now connected to the distribution network via cables that have a combined neutral and earth conductor into the property, giving us a TNCS supply. These come from the street, where they connect to the main supply cable from your local transformer via joint boxes that are buried in the ground. At the point where this connection is made, the DSO connect the combined neutral and earth conductor directly to the general mass of earth. That's the earth we walk around on. Because they do this at every connection from the supply cable, it gives us multiple earth connections along the protective conductor. That's where we get the expression protective multiple earthing, or PME. Unfortunately, some of these connections to the main supply cable are starting to fail. When this happens, the earth and neutral connection to the property can be lost, and because we've lost the protective earth and neutral connection, we refer to this as a PEN fault. The prospect of this was especially worrying when EVs started to become popular, because you'd end up with a big lump of metal on the driveway at 230 volts. This led directly to Amendment 1 of the 18th edition. But even with that hole in the regs plugged, a PEN fault can still cause other serious problems, because in older properties where most of the aged supply connections are failing, there's very often a metallic pipe coming into the property carrying water, and maybe another bringing in gas. Much like the supply cable running down the street, these pipes connect to a main pipe to supply the property with the resource that it carries. For simplicity in this video, we're just going to show the water pipe, not the gas pipe, although all the same principles apply. We're going to consider 2 different scenarios. In the first, we've got 2 properties side by side, both with an incoming water supply in metal tubes connected to a metal pipe between the properties. If the old creaky combined neutral and earth connection to the main supply cable has become disconnected, then a major problem becomes apparent. Or does it? I'm going to simulate this happening on my demo rig here. Now, please bear in mind that this setup is designed to be dangerous and wildly violates many parts of the regs and health and safety law in general. Please don't try to recreate this. We're in controlled conditions here, and I count my life as naught when compared to bringing you this potentially life-saving information. Does that make me a hero? Yes. Now, get ready for this, because it's where things start to get really dangerous. I'm going to operate this switch down here, and it will disconnect the combined neutral and earth connection to this simulated property. Okay, hold on to your hats. Here we go, and... yeah. Well, that was anticlimactic, wasn't it? I've just introduced a potentially life-threatening fault into this system, and nothing's tripped. Everything's working as it was before. There's not even a flicker of a light or anything else to indicate that there's a huge problem here. And that's largely because of the way that TNCS systems work, as well as the issue of this common water pipe between buildings. Let's trace where the electricity travels and figure out what's happened. So it comes up from the street and passes through the fuse in the service head, through the meter and the consumer unit, down a circuit and through a load, and then comes back down the neutral through all the same bits until it gets to here. Now, this is the point where the neutral and earth conductors are combined. They literally join together and become the same conductor. Now, however, the current can't carry on down the supply cable because it's got nowhere to go. However, it does have this handy earthing conductor to travel along. Then it finds it can flow along this bonding conductor to this metallic water pipe. It can now leave the property and travel along the pipe. What's this? Next door's water pipe. It travels along there, comes to the neighbour's bonding conductor, travels to the main earthing terminal, and from there to the service head, where, lo and behold, it can travel back down the neighbour's combined neutral and earth conductor in the supply cable and make its way back to the transformer. So the current that should flow down the neutral has become diverted through next door's supply. That's where we get the phrase diverted neutral current. It's worth noting that some of the current will find its way back to the transformer via the general mass of earth. However, as the path back will likely have a relatively high resistance and the path back via next door's earthing arrangement will be relatively low, the current will split in inverse proportion and the bulk of it will go via the low path. This can still become a problem even when we've got a plastic incomer. Let's discuss scenario 2. Here we've got one slightly more modern property with a plastic incoming pipe and the older property still with its incoming metal water pipe. If the same fault occurs, then we've got a pen fault, which is a problem, but there's no neutral current being diverted from a different property. A larger problem would occur if we lost the neutral here. Now, the neutral current from property A can't divert through the incoming plastic pipe, so it flows down the neutral as expected, but because it can't get back to the transformer, some of it will go through the general mass of Earth via the PME as it should do. However, as this metal pipe is buried in the ground and connected to the general mass of Earth along potentially a long distance, that means it could present as good a path, if not better, back to the transformer, and therefore a chunk of the current could flow along there as well, giving us diverted neutral current back through the earthing arrangement. There are a lot of different scenarios and situations where this could occur, and we've just looked at 2 examples. It's impossible to outline all the variations in a concise video, but however it's occurring, is it that big a deal? Well, there are a couple of dangers that this situation represents. One is a problem for the homeowner that will vary in degrees of seriousness. The other is hazardous to anyone doing electrical work. The problem for the homeowner is that the current flowing through the earthing conductors in their property might not be the end of the story. If there's a number of houses along this stretch and further faults occur in a certain way, then these conductors may end up carrying the full load current of several properties. That means this conductor may start to carry more current than it was ever designed for, and there's no protective device to halt that situation. While it may not necessarily cause a shock risk, that amount of current can generate some serious heat and could start a fire. The danger for anyone doing electrical work is that, much like myself at the start of the video, if I come along and disconnect this conductor to do some electrical work, then all of a sudden I'm handling a conductor that I might naturally assume is dead and safe to touch. But the reality is that this could be live at a high enough voltage to kill me. And it's not just the conductor or the earth bar that might be live at this voltage, it could also be the water pipe, the body of the consumer unit. In fact, anything that's connected to the earth terminal in one way or another. One way that I could detect this problem and potentially protect myself from the danger is, before disconnecting anything, just to pop a clamp meter around the main earthing conductor, the bonding conductor, or even the metallic water pipe. If there's a significant current reading, then it could be a sign that there is a problem. Unfortunately, like so many things in the electrical industry, it's not always that simple, because you might read a current flowing in these conductors even when everything is completely healthy. Let me explain how. Let's look back at scenario 1 with properties connected together as we've discussed, with supply cables on a TNCS system and a common metallic water pipe. Current will naturally flow through the earthing and bonding arrangement, and that's because when the current gets to the combined neutral and earth connection, it has multiple paths it can take back to the transformer. It can flow down the CNE conductor here, as you'd expect, but it also has a very low impedance path it can take along the bonding conductor to the water pipe, through next door's bonding conductor, main earthing terminal, and their CNE conductor as well. The current will split proportionally to the impedance offered by the route back, so the bulk of it will go the way we expect it to, but some of it will go back via the slightly higher impedance route of next door's connection. Of course, this is a very simplified picture. Next door's installation will also be sending current the way it should, which will affect how much of yours goes that way, and indeed the positions may reverse and more current comes back down your earthing arrangement than theirs. Extend it to multiple properties on the same cable and water pipe and you've got a situation where it becomes very difficult to know where the current will be flowing at any given moment. Indeed, in a healthy system, it doesn't actually matter. That current flowing through your earthing system and even through the water pipe doesn't cause any harm or even potential harm. In fact, we can demonstrate this in our industrial unit cum recording studio here. If we pop a clamp meter around our main earthing conductor here, we can see that there's a reasonably sized amount of current flowing through here. Now, this might lead you to think that there's a serious problem here, as we've outlined already in our demo rig, but actually, this is just the way a TNCS system works when you've got common metalwork between buildings. Here, it's as likely to be the bonded structural steel as much as the water pipes that's creating all the extra routes for the current. But we know it's not a problem, because when we remove the earthing conductor and measure the voltage between it and the earth terminal, the voltage is effectively 0, indicating that there's no serious problem here. And that's where we get our method for making sure that we don't have a live conductor that should definitely be dead. After performing the regular safe isolation procedure on an installation like we've done here, there's a number of further steps that you can take to reinforce your safety. The first is to get your clamp meter around any extraneous conductive parts that you can, like water and gas pipes, and around the bonding and main earthing conductors. If there's current flowing through any of them, then that may be an indication that there's an issue. But as we've seen in our headquarters, it's not a guarantee that there's a problem. To add an extra layer of protection to the process, you could get yourself one of these contact voltage detectors and pop it onto the earth metalwork in the property, both before and after disconnecting the earthing conductor. To be absolutely sure, you could very carefully, while wearing protective gloves and other appropriate PPE, disconnect the main earthing conductor and measure voltage between it and the main earthing terminal. If there's a significant voltage there, then very carefully simply reconnect it and contact the DSO to come out and investigate. Remember, if there is a significant current flowing through the protective conductor system when you disconnect and reconnect the conductor, it could create an arc, so make sure you're wearing all the relevant PPE before you do it. So how much of a risk is this hazard? Well, it is a very real danger and it is happening out there. Currently there's around 300 of these types of faults occurring every year, so not a huge figure. However, just one of these faults can affect multiple properties. This happened in Grimsby in 2023, where a single fault affected 500 homes. But there has to be a number of factors in place for it to happen. First of all, you need to have a metallic service feeding a property. Newer installations are far more likely to have plastic water and gas pipes supplying them, and for most of these installations, the bonding in place is completely pointless. Then you'd need to have a situation where the combined neutral and earth conductor has actually failed, followed by there being no other path back for the current to take. If multiple properties are tied to the metal incoming service, the current could well find its way back through one of those other connections. And if there's a sufficiently low earth path back to the transformer via the general mass of earth, this will help as well. It's a complex picture and it's almost impossible to outline all the different scenarios out there. But it is out there and it is dangerous, but it's not going to happen in every property that you go into. So take the extra precautions and it'll help keep you safe. Now that brings us nicely onto our next issue that's even more likely to raise its head, including on new builds, other sources of supply. Luden are now producing these bidirectional RCDs. They're critical in modern installations because they allow for the fact that we no longer just transfer energy into an electrical installation, we also transfer it out the other way because of the rise of the photovoltaic panel. There's been a lot of confusion around whether RCDs need to be bidirectional, especially with solar PV systems. In setups where solar panels feed an inverter, then a battery, and finally a consumer unit, RCD protection is required, especially when cables are buried shallowly in walls. Most RCBOs have marked terminals, line in, line out, and so forth, meaning they're unidirectional and must be connected correctly to work. If connected incorrectly and current flows backwards from a solar PV system, for instance, the device can become damaged. This is because the internal PCB and solenoid may remain energized after a fault, risking failure to trip on subsequent faults. The solution? Use a bidirectional RCBO with a mechanically linked contact that disconnects the PCB regardless of power direction. However, being double pole or neutral switching doesn't automatically make an RCBO bidirectional. Always check the datasheet. This issue prompted a rare urgent update to the 18th edition of BS 7671. Regulation 530.3.201 states that the choice of protective device must consider whether unidirectional or bidirectional device is appropriate. It doesn't ban unidirectional devices, they're still suitable for circuits without power generating equipment. However, this led to electricians panicking a bit and starting to specify and install bidirectional devices on every circuit. This isn't necessary and can be a bit of an issue as there is a slight cost difference between the two. The bottom line is, if there's no power generation on the circuit, a unidirectional RCBO is fine and probably cheaper. If there is, use a bidirectional one. Note that we're referring to circuit there, not installation. This building has PV installed, but it isn't connected through the internal consumer unit and therefore no bidirectional devices are required here. Terminal markings and datasheets will help you choose correctly. So why are we addressing this in a video about safe isolation? Well, because it neatly highlights a potentially dangerous situation whereby you've isolated an electrical installation, again following that tried and tested process, and yet when you open up the board and get to work, it turns out that there's still some very, very live parts being fed by the still happily operating and generating PV system on the roof. So how do we protect ourselves and others from this hazard? Well, safety begins with us, so the first thing to do is to make sure that the installations we work on comply with the regs, in this case specifically 514.15 under the heading Warning Notice, Alternative or Additional Supplies. Regulation 514.15.1 reads, where an installation includes alternative or additional sources of supply, warning notices shall be affixed at the following locations in the installation: at the origin of the installation, at the meter position if remote from the origin, at the consumer unit or distribution board to which the alternative or additional sources are connected, at all points of isolation of all sources of supply. The warning notice shall be durably marked and identify the relevant points of isolation. We're given an example of this in figure 11E of Appendix 11. Hopefully the electrician who went before us is every bit as diligent as we are and has installed bidirectional devices where necessary and stuck warning notices in all the relevant places. What though if they were slightly less than diligent? Well, the first thing to do is to make sure you've had a good scout around the property looking for other sources of supply. Photovoltaics are hard to miss, but there may be other things like backup generators on some installs. There should be isolators on or near power generating equipment to disconnect the outgoing supply from them, so operate these and lock them off with signage as usual. Then, as part of your safe isolation process, make sure you've tested the seemingly outgoing conductors on the circuits within the consumer unit you're isolating. Following these steps should help to keep you safe. Next up is that most untouchable of parts in the electrical installation, the service head. Recently we had to call out the DSO to take a look at our incoming supply while we were having solar panels installed, and he appeared looking like he was getting ready for interstellar travel. This made us wonder why such extreme measures might need to be taken, so we started looking at this seemingly innocent area and how it could affect us. The electrical service head, often referred to as the cutout, is the first point of connection between the supply from the distribution supply operator, or DSO, and a customer's installation. When undertaking certain types of work such as replacing a consumer unit or installing an additional one for an EV charger, you may need to isolate the meter tails, that's the cables running from the electricity meter into the consumer unit. If you're lucky, a double pole isolator may already be installed. This is common in newer properties and allows for a safe, convenient disconnection of the supply. However, if no isolator is present, the only way to isolate the supply is by removing the service fuse, which requires breaking the supplier's seal. And this is where confusion and misinformation often take over. To be absolutely clear, only the DSO, the energy supplier, or a licensed safe isolation provider, or SIP, can legally remove this seal and isolate the supply. A SIP is an authorised third-party provider who carries out safe disconnection of supply equipment on behalf of the DSO or energy supplier. While some DSOs offer schemes that allow electricians to perform certain types of isolation work, it's important to understand that these schemes do not permit the removal of seals on electricity meters. That responsibility remains strictly with the DSO or the supplier. Although typically sealed and considered not to be tampered with, these components can present serious hazards when they become damaged or degraded over time. For electricians, understanding these dangers and following appropriate precautions is critical for personal safety and compliance with regulations. If you're working near supply equipment, remember the cable and service head may be over 100 years old and might not have been inspected for decades. That's why it's essential to follow industry safety guidance. Always wear insulated gloves, use a full face visor, and assess the condition of the equipment before touching anything. The electricity supply industry uses asset condition codes to identify and classify faults in supply equipment. These are particularly important for electricians working around older infrastructure and should be well understood. The following are examples of Category A emergency codes, conditions which present an immediate danger to life or property. If you come across any of the following, do not proceed. These are critical safety faults and must be reported immediately to the DSO supplying the property. We'll leave a link to the full guidance provided to meter installers in the CPD notes so you can explore the asset condition codes and associated actions in more detail. Older service heads, particularly those installed during the mid-20th century, often use casings made from what's called a phenolic resin. Over time, exposure to heat cycles and environmental factors like moisture and UV radiation causes the phenolic material to degrade. This can lead to embrittlement and even cracking, exposing live components. Even more dangerous and extremely surprising is that the plastic type material itself can become conductive and therefore live under certain circumstances. If you come across older black coloured service heads, then grab yourself a voltage contact indicator like this one from TIS and check all the different parts of it, especially the parts you might need to touch like the fuse carriers. If at any point it shows that the surface is live, then contact the DSO for that area. The more modern grey cutouts are a different material and are not prone to this type of issue. The cable insulation feeding into service heads is also susceptible to age-related degradation. The most common issues include cracking or splitting of the outer sheath, loss of mechanical strength and shrinkage, which exposes conductive elements. In older installations using vulcanized rubber or cloth-based insulation, deterioration is often accelerated by heat and mechanical stress. Exposed conductors can create the risk of electric shock, particularly in damp environments or where conductive dust is present. The main fuse carrier, often BS88 types, within the service head may show signs of thermal damage due to prolonged overcurrent conditions or loose terminal connections. Cracked or warped fuse holders may no longer provide a safe enclosure for live parts. In some cases, the fuse may be improperly seated, allowing arcing to occur if the assembly is disturbed. It's not uncommon for cracked fuse holders to dislodge when disturbed, especially during meter changeovers or when installing isolators. A live fuse making a poor connection within the service head presents an obvious risk of electrocution or fire. Tampering, age or poor maintenance can result in missing or broken seals on cutouts, and while seals are primarily used to prevent unauthorised access, their absence may also indicate that the equipment has been previously disturbed, possibly by unqualified persons. Missing seals are a red flag for internal damage, loose terminals or improperly fitted components. Electrically, a cutout with no seal can pose a danger due to unintentional movement or access to live components, especially during routine inspections or when adjacent works are being performed. Older installations may also contain asbestos, particularly in fuse carriers, backboards and internal linings. If you suspect any component may contain asbestos, do not disturb it. Stop work immediately and report it to the relevant authority or DSO. Appendix 6 of BS 7671 gives us a model checklist of items to inspect on both initial verification and during periodic inspections. It informs us that item 1 is to check the condition of consumer's intake equipment and suggests that you check the consumer's isolator, where present, and the consumer's meter tails. It also advises that where inadequacies in the intake equipment are encountered, which may result in a dangerous or potentially dangerous situation, it is recommended that the person ordering the work informs the appropriate authority. It's a little more expansive in the periodic inspection section, suggesting that we inspect the service cable, the service head, the earthing arrangements, meter tails, metering equipment, and the isolator where present. So there's a slightly broader range of things suggested there. However, it makes sense to apply the longer list on initial verification anyway. After all, a rewire or a refurb could require connecting to an older intake system. Either way, if you find anything within these categories that aren't right, then it's time to contact the DSO and get them to come and fix it. You mustn't attempt to remove or alter DSO-owned service heads or seals. If a defect or hazard is suspected, report it to the relevant DSO. They are responsible for addressing service head issues, including fuse replacement and component integrity. When you're working near the intake, you should always use Class 2 insulated tools, arc-rated gloves and safety glasses. Even with the main fuse in place, faults in degraded service heads can result in arc flashes or unintentional energization of nearby equipment. Where permitted and coordinated with the DNO, installing an accessible double pole isolation switch downstream of the meter is a highly recommended practice. This allows safe isolation of the customer's installation without disturbing DSO equipment. Now, there's one final and often overlooked risk that electricians need to be aware of when completing safe isolation procedures, and that's the risk of energy theft, specifically through meter bypassing. This is a serious and growing crime where individuals tamper with or bypass the electricity meter to obtain energy without paying for it. Naturally, those who engage in this activity have no regard for regulations or electrical safety, which can create extremely hazardous conditions for anyone working on the installation. There have been documented cases where electricians carried out all the correct safe isolation procedures only to receive an electric shock from a backfed circuit, a result of a bypassed meter supplying power outside of the expected paths. And it's important to understand that energy thieves can adopt very sophisticated methods. In one case reported last year, a property had been supplied by a completely new and illegal connection taken directly from the underground supply cable in the street, bypassing the meter entirely. These kinds of setups may not be obvious at first glance, but can present serious hidden dangers to anyone working on the system. To protect yourself, it's essential to treat energy theft as a potential hazard, just like any other source of uncontrolled or unexpected supply. Always carry out additional voltage tests at all parts of the consumer unit or distribution board, especially before touching conductors that are believed to be safely isolated. Warning signs of meter bypassing or tampering include missing seals or covers on metering or supply equipment, visible damage to the electricity meter casing, altered or suspicious cabling around the meter or service head, excessive signs of DIY work near the meter or isolator, and unexpected secondary feeds entering the installation from unusual routes. If you suspect signs of energy theft, you can report it anonymously via the Stay Energy Safe website. We'll include a link in the description or CPD notes. So it turns out there's a lot to think about to keep yourself safe when it comes to isolating the supply or supplies to a property. Current may be coming at you from unexpected directions, safety equipment could betray you, and illicit activity can put you at risk. Take additional precautions, never ever assume, and test everything. If you're watching this on our training platform, answer the multiple choice questions that follow to get your CPD certificate. If you're watching it anywhere else, click the link in the description to access our free training platform. All that remains in this video is to say thank you very much for watching.